So, given that, what can we do with those PCR values? The answer really is attestation. So, when I talk about attestation, I mean the presentation of evidence that can be verified. I'm not just trusting blindly a claim. I can actually look at that and evaluate it about a machine to some remote party. So in the TPM context, when I talk about evidence, that almost always means, here, have some PCR values. Because that is our evidence about system state. Now we can augment those PCR values with more than just the boot time measurements or the DRTM measurements. And that's a lot of what I'm going to talk about in this section. The verifier, who is, depending on whose papers you read, can also be called the appraiser, so you should be familiar with both of those terms, can inspect the PCRs and verify the chain of trust from some root of trust for measurement up through whatever values the verifier cares about. And again, you can't just jump straight to the high-level components you care about. You do have to verify the low-level measurements first that were used to generate that high-level measurement, or the high-level measurement is not trustworthy. Your primary tool for getting PCR values is the quote, which is that signed reported PCR values, but any kind of cryptographically verifiable PCR state evidence counts. And that cryptographically verifiable matters. Almost everything that you can do involving PCR constraints on a TPM can be used for attestation, but not quite all. And I'll talk about that. So here is, in a little more detail, a picture of a quote. This is still abstracted. Now that said, when I say quote at the front there, in the actual literal data structure, there is in fact the string QUOT, or QUT2, depending on which version of quote you're doing. But basically, there's some static data structure that basically says, hi, I'm a TPM quote. There's a field that contains 20 bytes of nonce, which is just user. From the TPM's perspective, you handed me user data, I'm going to treat it as a nonce. 20 bytes of data, it goes to this field and I sign it. That's all. I'm not going to think about it. Then you hand the TPM, when you request a quote, a PCR selection, where you say, which PCRs would I like to quote? And it doesn't have to be 0 through 24. I can say, I want PCR. Yeah, all I care about is the static root of trust for measurement. I can say, please quote me 0 through 15. If all I care about is the DRTM, I can say, please quote me 17 through 19. Or if I'm doing fancy tricks, I can take pretty much any subset of PCRs. You know, it's just an arbitrary bitmap. You pick. The TPM will take that selection of PCRs and the hashes in it, hash them together, so it's just basically a hash signature, and stick that into the quote data structure, and then sign the entire thing. And the reason I say sign that with an AIK there, even though the TPM will let you sign it with a signing key or a legacy key, is you really, really don't want to sign this with signing or a legacy key. Because signing keys and legacy keys can also be used to sign user data. Now, there is one kind of signing key that is designed to not let quotes be forgeable. Unfortunately, that's the one that turns out to have a SHA-1 attack on it.
Oh.
So the only signing keys that you ought to be using are the ones where I cannot distinguish it. And I'm going to go into much more detail about signing keys shortly, but don't use signing keys to sign quotes in today's world. It's just a bad idea. So again, we have that nonce for freshness and the hash of the PCR values, which is our state report, and then we have a signature so we know that it actually came from a TPM. So how do we actually use this? The most basic of all attestation protocols is the one where the appraiser sends a challenge that has a nonce in it for freshness and the PCR selection. And the attester is going to reply with that quote data structure containing that nonce and that set of PCRs. And realistically, when I just said here include the quote, and you will see this a lot, people just say use a quote. The quote is a signed hash. You are going to have to send both the signed hash and enough information for the verifier to actually verify it, because the verifier, unless you are very predictable, does not actually know what your PCR values are in advance. So having them determine, are you using the correct quote, you do actually need to provide them with enough data that they can do their own hash and make sure they're the same. So there is one open source quote utility out there, which is actually from John Ransdell at MITRE, who put together TPM quote tools. His version actually does assume that you've basically taken a master quote at some point in time, and it will just keep checking to make sure the nonce is right, and then let you know when it fails. But you can't tell there, did one PCR change, did all of the PCRs change, what were the PCR values? You're just saying, is the quote today effectively the same as the quote yesterday? So you can do that kind of verification. You're not going to get detailed information if you try doing that. So the attester, when they get that request, does have some choices they can make. In particular, this is the only chance the attester really gets to say, do I want to tell you that information? Because those PCR values do contain information about the state of the machine. So the attester, ideally, if they actually think the PCR values matter, should probably check and make sure that this attester, the appraiser, is one that they trust and one that they want to tell what operating system they're running. And the appraiser looks at the results and says, first, they need to check the signature, make sure, yes, this is a valid quote structure, it's from a legitimate TPM, and it is signed by a key that I actually trust to sign quotes. Is the nonce actually the same nonce that I provided? Because that's really a replay detection mechanism. And are the PCR values in some state that I approve of? Now, you don't necessarily have to do that last step. You can say, well, you've done a quote and just store the data. This is what the host integrity startup system does, is it does a quote, and it says, I don't know how to interpret this, I'll just stick it into the database, and eventually a human will come along and look at it. But fundamentally, this is attestation with a quote. You look a little perplexed. Is there any...
I'm a little confused. So it initiates with the attester? Or
Yeah.
it
initiates it with the appraiser.
with the appraiser, and then the appraiser sends it over to the attester, and...
So you can think of this as a challenge response system.
Yeah.
That's all it is.
Okay.
It's a challenge response system with some funky formatting attached.
Okay.
Now, this is just an example protocol using a quote.
Okay.
I can, like, the variation of this that is attester initiated.
Yep.
I can do that by saying, "Hi, please quote me. Please challenge me."
Okay.
This is not the only way to do this, and in fact, often you will see quotes embedded in more complicated protocols because, for example, nothing here tells the attester who's asking the question.
Right.
This is not a mutual attestation protocol. This is the little puzzle piece of what does a quote look like in a transaction.
Okay.
So in the real world, we usually see some kind of session initiation, some kind of exchange of identities. You will sometimes see what's called mutual attestation, where the appraiser and the attester both like challenge each other and both get a quote back.
Okay.
So there's a lot of variations here.
Okay. Okay.
This is just an example of what the transaction can look like.
Okay.
Boiled down to its simplest possible. In fact, generally I wouldn't recommend using that in isolation because it. But this is, by the way, this simple structure is basically the TPM's perspective on what a quote looks like. It doesn't have any context.
Okay.
From the TPM's perspective, somebody said, here's a nonce and a PCR selection, and it replied with a quote.
Okay.
It doesn't know any better. You can actually, if you want to, in most systems, set the TPM driver up such that it will, in fact, respond to a request like this across the network.
Oh, really?
Yes. We do not generally recommend doing this, but you can, with no extra protocol overhead involved. It's not even very hard to do in a lot of systems. So when I say we don't really recommend doing this, be aware that this is actually very easy to do anyway. And if all you care about is I, as the IT department, want to get a sense of what the state of my machines are. I'm not worried about an adversary making sense of this mess, because really if they want to know whether the machine is running Windows, they will just ping it or log in. You can set it up to respond arbitrarily on the network if you want to minimize the amount of software you're running and the amount of connections you're initiating, but realistically, this is not a use case I've seen anyone have major demand for. But it is one that you can do if you want, and I've seen researchers use it because, frankly, they were lazy and didn't want to write any extra software to maintain, to act like a server. So, sometimes we want to go beyond what the measurement infrastructure will do by default. Maybe we want to add measurements from applications we've installed. Maybe we've got a configuration checker or an antivirus, or we're living in a beautiful virtual world with kernel state integrity checkers. All of those measurements are not default part of the PCRs because they're not part of that boot chain sequence or that DRTM handoff control sequence. Maybe we want to associate certain application data with a good state. So we don't just want to say, hi, this financial report is from machine X. We want to say, this financial report was sent by machine X when I was running the right financial software. Or perhaps we want to tie external data, by which I mean TPM external data, or maybe literally external data, to this machine. So I've got a smart card in a reader that's attached to my machine. That smart card reader was not part of my boot sequence, and the smart card certainly wasn't. But I would like to say I've done a smart card authentication sequence, and I want to tie that to when the smart card authenticated, my machine was good. So there are a lot of potential scenarios where I want to go beyond, is this machine good, or where did this data come from, into when this data was generated or sent to me, was the machine good? Now, I will note, when this data was generated is actually very, very difficult because, well, if you think about it, I generate data, it's sitting on my hard drive or on my memory. If I come along in 2 days and take that report and change the timestamp in it and send it and sign it, I can't tell whether it was actually generated today or 2 days ago. What I can say is at the point that it was signed, was the machine good? And this is part of where that you always want to evaluate in an ideal world. All of the chain from the initial boot up to wherever you're running, because that can make the difference between, is this just data from this machine or sent via this machine, possibly from somewhere else, or do I trust this software to not have tried to fork it? That's hard. That's our holy grail. We're not getting there anytime soon, but we should be aware that that's out in the distance, and we always do want to check that sequence. So there's several ways to do this, the simplest of which is to incorporate the user data in a quote. So let's talk about all of our options. The naive way to include user data in a quote is to say, we've got a nonce, and the nonce field is labeled 20 bytes of user data. Therefore, clearly, we should put the hash of whatever file we want to measure into the nonce field. Don't do this. And when I say this is the naive way of doing it, people really do. I have seen actual published protocols that do this, and I'm going to go into that in a moment. The problem is that the nonce is intended for freshness. It is not intended to be a signature. And if you do this, you open yourself up to a man-in-the-middle attack. Because, let's say I'm system A, I want to challenge some system to sign data for me and identify themselves while they're at it and tell me that they're in the correct state. So I say, here's a challenge, here's your nonce, and by the way, here is the data I want you to sign, or a request for the data I want you to sign. That malicious adversary can receive this request and turn around to some other system B and say, hi, I just want a perfectly ordinary quote, and here is my nonce, which is itself a combination of the first nonce and the data. Now, from system B's perspective, it can't tell the difference between an utterly random nonce and a random nonce that happens to have been, combined with some data. It's random values. It can't evaluate it. So B happily signs a quote because it's a good cooperative citizen. It is happy to perform an attestation for somebody else. That gets forwarded back to A. And from A's perspective, B has just signed data. From B's perspective, it never even heard of the data. It performed a quote. So now we have this massive trust mismatch, which an adversary can take all kinds of advantage of. And this is an actual flaw in TNC, in the PTS to IF-M protocol. We brought it to their attention, and their response was, why would anyone ever use more quote protocol than ours on the network? As long as everyone's using our protocol, this isn't a problem. Don't do that, really. So, for one thing, the TPM cannot possibly be taught about protocols that layer meaning onto the nonce, which means that there's always going to be some point at which somebody can pull this attack, even if they're on the same system. Even if you do trust your system to behave properly, as long as anyone on your network who is running a TPM that you trust will ever answer any other quote protocol, even if they're all layering nonces but differently, especially if they're all layering nonces but differently, your protocol will break and you won't have any way of knowing. So this is not a good idea. Do not do this, really. So the safe way to include user data is to include it in PCR. That's what the PCRs are for. They store data. So you can extend that user-generated data into some otherwise unused PCR. And it is worth noting that although quotes, we default to assuming that if you're using quotes at all, you will generally respond to requests for quotes with some frequency directly from the network with minimal evaluation of should I do it or not. At best, you're usually going to say, should I give it to you or not? Well, nobody in their right mind answers requests from the internet to say, please extend PCR 15 for me. That's not the way that these are meant to be used. So, unlike a quote, we cannot just say, extend this PCR with arbitrary data. Yes, an adversary who is local, who is network controlled could do this, but you just raised the bar noticeably. You actually have to be on the computer to pull an attack. It's remotely verifiable, because hey, I can do a quote and read what's in the PCR. That's very straightforward. And there's no real change of meaning as long as you're not putting your data into a PCR that already has meaning. Of those 24 PCRs in that chart I showed you, only about 10 of them are really used today with any given meaning. Even if you've turned on something like Trusted Grub, which uses way more than the default set in a meaningful fashion, you're still looking about 17 of them have meaning, even if you're generous in using everything. So that still gives you some noticeable room to add your own data without causing anybody else to be deceived. So it is often very wise to make sure that whatever data you're extending into this also has its own freshness so that I can't replay the data while using a fresh extend. If I'm generating a report, knowing whether it's today's antivirus report versus last week's antivirus report, if I'm just looking at the quote may be fresh. Whether or not the data is fresh depends on whether the data includes freshness, but there's a limit to how much we can do here. In general, again, nonces are much better for freshness than timestamps, because timestamps are predictable. I can forward them very easily. And I will note that these can be used as a long-term signature. The nonce doesn't have any meaning if I'm using a quote as a long-term signature. Fresh, there's no meaning for fresh. But what it does tell me is that at the time this quote was generated, whatever it may have been, these were the PCR values. So that means that if I'm including like a financial report in a PCR, at the time that this financial report was signed, these were the PCR values. That's still potentially a very useful thing to know, even if I don't have any data from within the quote as to whether that was today or last week or last year. I still know that this report was generated in an honest state.
So I may have remembered this wrong, but I thought PCRs reset themselves?
They
So
do.
so how do you save that?
You don't save the PCRs, you save the quote.
So the quote is stored
It's
where you determine
it's
where...
data structure. If I send to some central repository of data,
Yep.
a quote along with and PCR 15 in this quote,
yep.
it contains a hash of this report.
Yep.
That combination of quote and report can be forwarded around just like a combination of report and signature can be forwarded around.
Okay.
It's just that this signature also includes some extra metadata, effectively, about what the state of the machine was at the time that was signed.
Okay.
So, I talked earlier about the fact that we have resettable and non-resettable PCRs. And which one you choose to put user data in is actually critically important. Resettable PCRs, you can go back to a known value on fairly frequently. This actually makes them very useful for user data. Because if I am, for example, using a quote to sign, part of an SSL session operation, I don't want the history of every SSL session I've ever tried to initiate stored in a PCR. That is leaking information all over the place, and really nobody cares, and my verification chain is then going to be a pain in the neck. Even if I'm doing, signing reports, I don't necessarily want a list of every report I've signed on boot, and now the verifier needs to know how many reports I've signed since this boot and actually track that. In comparison, if I use a freely resettable PCR, I can reset the PCR, put that report hash in, do a quote, reset it again, and now I have a clean signature over this one value. So resettable PCRs are actually tremendously useful if you are using quotes to sign user data. Non-resettable PCRs are still very valuable because they can give you an audit log. Usually we want to see this if we are expecting data to be updated between challenges. So if I've got some operation that is meant to run once an hour, and I'm only challenging the machine once a day, I can use a non-resettable PCR. In fact, I generally want to use a non-resettable PCR so I can get some record of what's happened over the course of the day. But that said, there's a big weakness here, which is that we can't tell when a machine reboots. We can tell whether a machine has rebooted. We can't tell how many times it's rebooted, and we can't tell when that happened. So, there is a tick counter, so we can get some idea of it. I do not actually have a very good sense of, over the course of a full day, how accurate is that tick counter. But this can give you something where if you're doing periodic challenges, I can get some idea of, does this correspond to the record the server has at the times that I checked in? Does it look reasonable? It's much more for a sanity check. But you can tell that's very much a special case when it comes to user data updates. And we mostly see people proposing that as sort of a stopgap measure if realistically they want to be checking the machine state once every 5 minutes, and there's not a server that's going to be running a challenge once every 5 minutes. That would be awfully high overhead.
Can you have two sets of PCRs and configure one as resettable and one as non-resettable?
There are 24 PCRs.
Okay,
so you can use whichever ones you like. We generally recommend using ones that nobody already has a meaning for. There are 2 freely resettable PCRs, which I want to say are 15 and 23.
Okay.
They're in that chart, so you can flip back and look. Those 2 are perfect for one-off data signatures. Anyone can reset them. Anyone can extend them, so you don't even have to worry about what locality you're in.
Okay.
For non-resettable ones, you are probably looking at the unused portion of those static root of trust per measurement window. That 0 through 14 are nobody can reset, anyone can extend.
Okay.
Most of the time, and the largest number of those that I know that anyone uses is Trusted Grub, which uses 0 through 13.
Oh.
So that's a window of 1 PCR, even if you're maxing out that. That is not currently used for anything. And if you're willing to start getting into fun with locality, you've got several more options because nobody is using those trusted OS controlled locality PCRs right now. Now, problem is those are technically resettable.
Yeah.
So, yeah. Choosing your PCRs wisely matters, and much more so for the non-resettable ones than the resettable ones. Even if you've got 6 different applications that all want to use resettable PCRs, as long as the general behavior is reset the PCR, extend your data. Even if not all of them behave nicely and reset it again when they're done, you're not going to have any problems from that because you reset it. You don't care what else was in it before. You just need to make sure that you've got a relatively atomic reset then extend, so nobody else is doing race conditions with you. Okay. So that is how you can use quotes to do an attestation, potentially also with user data included. There are other ways to do it. You can also use the fact that you can put PCR constraints on keys and on data. Now, in both of these cases, you've got a fairly hefty requirement, which is that you need to know in advance what the PCR values that you wish to attest to are. Because after all, you're constraining a key to some set of PCR values. If those set of PCR values never exist, that key is useless, and you certainly can't attest to the fact that they do exist. As a side note, in this entire section, I'm going to talk about PCR constraints. In 1.2 TPMs, the PCR selection data structure also includes a locality selection data structure. So anytime I say you can lock this to you can constrain the PCRs this is accessible in, you can also constrain the locality this is accessible in. Usually, this is something that DRTM applications use. So you can say this key is only accessible in locality 3. Well, now you've said this is only accessible to things that have been launched by the DRTM. That's tremendously useful. I'm not going to talk about it in detail because PCR and locality constraints is extra words. To be perfectly honest here. And for the most part, locality is a special purpose constraint, but be aware that that's there. So we mentioned yesterday when talking about creating TPM keys that any TPM key can have PCR constraints associated with it. It's part of the creation structure. They never change. Again, in 2.0, that gets more complicated and updates are possible. Those keys can only be used when the PCRs match the constraints, and we've got this wonderful certified key operation that allows a remote party to confirm what the constraints on that key are because the TPM signed a report about that key and said, look, this is the type of key, here are the constraints on it. So that means that if I create a key with some PCR constraints X and certify it, that every time that key is used, a remote party can say, I know that at the time the key was used, the PCRs contained X. Very simple. Not very complicated logic, and I can use that with any kind of key. So when this data was signed, PCRs X, state X held. That's that quote long-term quote state verification use case I was talking about, but here I can use it for any signing key. So I don't need to be constrained to extending a PCR, and I can use arbitrary user data without any, complex information there. So if I've got a key that I intend to only be used to sign data coming out of Flickr, I could say, here's the PCR constraints on it, and here's a quote, and now I've got this extra nonce that I need to send a log even though nobody's using it because it's not being used for freshness. Or I could say, I don't care. This is a signed report. I signed it with a signing key, and the signing key said I'm only useful when by a good Flickr application because it's locality 3 and it has the following constraints on it. So there's a lot of flexibility there. And it's very good if you're talking about, I want to show that I've handled sensitive data properly. And it's very good if you are doing, for example, I want an application that certifies keys that are not TPM keys. Which is to say, that's sensitive data. A certificate needs to be treated honestly. This is one of the things we talk about virtualization. This is actually a trick we use. is to say whatever the application that we trust to create virtual TPMs has to, that's a sensitive piece of data to handle, and we want to remotely prove at any point in the future that when this VTPM was created, the creator was in a good state. When this data was encrypted, this was true. This is mostly useful if you're talking about data handling tracking. So I want to know that when this data was stored for me, it was stored by me. You know, I've got a machine that may reboot into a bad state, or I don't trust that my hard drive is always under my control. Well, at least I know when I decrypt this data, if it was encrypted in a good state, that means that I created it in my previous incarnation, no matter what's happened in between. And I will note you can only do this one locally. Technically, encrypting data uses a public key, not a private key. So it's not as though I can really say that I'm using the key in question, but the seal data structure, which I'll talk about a little more in the next lecture, does record the PCR state when it was created, and that does require that those constraints hold. So we can do this sort of operation as long as we're doing it on one platform. And when this data was decrypted, the following will be true. So this means that I can package up data, which might be data for processing by a secure application. It might be a software update. It might be like anything where I want to say the recipient will handle this data properly. Private information, I want to make sure that there's an appropriate HIPAA-compliant application on the other end. I can encrypt the data with a particular set of PCR constraints and send it across the wire, and now the recipient needs to be, I know that unless that holds, it will be junk. So, sealing and binding both allow PCR constraints on data, although with binding, you are really stuck with constraints on the key, not on the data itself. So this is primarily useful for data protection because you want to know the target state and the target machine when the data is decrypted. And it means that you are moving away from simultaneous communication. And we previously talked about, signatures can say at the time this was signed, this is the case. This is sort of the reverse version where I want to say, at the time this was created, I don't care when you open it, but I just want to make sure you're good when you do. And I can do that day in advance, weeks in advance, months in advance. These can be published in the New York Times, and I can still be sure that whenever it's opened, you're going to be in a good state. If you have very predictable PCRs, then you can encrypt to a future state. Today, I have PCRs here, I do a quote to you, you can say, I'm going to encrypt to those PCRs, and whatever state you're in, I can be sure you're still in it. If you can predict the PCRs when you, for example, start your DRTM, if you can predict the PCRs when you update your software, I can start doing cooler tricks. So that I can say, if I am a Flickr application, the DRTM has been launched, and I want to encrypt data such that only another Flickr application on the same machine can access it, I can do that as long as I know what the measurements ought to be when that Flickr application is running. So there are tricks that we can do here where we can encrypt to specific states. And in fact, we can use this to encrypt data to the machine while it's booting. This data is only accessible to the bootloader. Why? Because after the bootloader runs, the PCRs change. Yeah, those are special purpose applications, but if you want them, you really want them. And that's really the summary of most of these PCR constraint games, is the vast majority of the time it's too fragile, you don't want to do it. But if you need that feature, it's worth dealing with the fragility because it's so powerful. So I said earlier that in general, if PCRs are constrained, we can use it for attestation. The big exception to that is NVRAM. Regions of NVRAM can be constrained by the owner to PCR values, but we cannot use the constraints on NVRAM to attest to a remote party because a remote party has no way of knowing what the constraints on NVRAM are. The owner set them, and there's no certificates about that. There's no TPM-supported way of saying this was configured properly. Now, you can theoretically have the owner independently create a certificate that says, I, Joe Bob owner, I, the IT department, say that on machine X, I have configured NVRAM such that this particular piece of data is only available. But now you're trying to certify, reasonably, that probably means, if access to NVRAM is what you're proving, that probably means there needs to be a secret in there, otherwise there's nothing to prove. And now you're trying to certify a secret to somebody else. And keep in mind, NVRAM is tiny. We're talking about maybe 2K at most. So chances are you're not storing an entire private key pair in there. Chances are you're storing a hash of a public key for verification. You are not realistically putting a secret that you can verify without knowing the secret in NVRAM. So this is not really designed for attestation. This is really designed for verification purposes and owner helpful. This is not an attestation use case. Unless you're the owner. If you're the owner, you know the secret that you put in there already. You don't need to certify anything to yourself. You probably can actually say, you've decrypted my penguin picture properly. I know that you're in a good state.
Yeah.
But realistically, you can do almost anything that's about NVRAM access with a decryption operation, get the same assurance and much more certifiability. So that is attestation in a nutshell. Again, the whole point of attestation is providing evidence that a remote party can verify about a state of a machine, and any verifiable report about PCR contents, whether that be a quote or certificates about a key, can be used for attestation. So, do we have any questions on the attestation portion of the program? Question, neat. Why not for remote attestation again? So, the reason you can't use NVRAM for remote attestation is that if I'm a remote party, I don't have any way of verifying what the configuration of your NVRAM is. PCRs, I know what the constraints on access are, and I can a TPM will certify what the values in the PCRs are, whether that is for a quote or whether that is for a certified key certificate. There's no equivalent to a certified key certificate for NVRAM, and even if there were, proving access to a region of memory pretty much involves you have to have a secret in it, and now you have to prove that you have access to a secret. Great if you're the person who put the secret there, not so great if you're anyone else.